Hello, in this video I'm going to go over how to configure and send a character through the Zynq's UART module with an assembly program. The Zynq has two UART modules, UART 0 and UART 1. UART 0 is hooked up to an ESP32 Bluetooth Wi-Fi chip, and UART 1 is hooked up to an FTDI USB UART bridge. This lets a PC with a normal USB connection communicate with the Zynq chip over a UART connection. UART is a character-oriented, full duplex communication protocol, meaning characters are sent one at a time, but they can be sent and received at the same time. Sending and receiving characters over UART in the Zynq revolves around two data structures, a transmit FIFO and a receive FIFO. These are first in, first out queues, and data written into them will be read out in the order they are written. That is, if you write data to the transmit FIFO, it will be sent out in order over the UART, and similarly, data received into the receive FIFO will be read out in the order it has been received. The UART control register is used to enable, disable, and reset the transmitter and receiver in the UART module. To reset the module, the transmit and reset bits in the control register need to be set to 1. After these are set, they will clear automatically when the reset's complete. You need to wait for this to happen before you can configure the rest of the module. To enable the transmitter, write 1 to the transmit enable bit. To enable the receiver, similarly write 1 to the receiver enable bit. These are bits 4 for the transmitter enable and bits 2 for the receiver enable. The UART mode register is used to configure how data is formatted when sending and receiving characters over the channel. Lets you select the number of stop bits, whether or not there's parity, and if the parity is even or odd, and the number of bits per character during a transmission. Also lets you select the clock which is used to generate a time base for the UART reception and transmission. In this video, I'm going to configure the UART module to have one stop bit, no parity, 8 bits per character, and to use the 100 MHz clock for generating a baud rate. The only setting I'm using that's not at its default value is parity. Because I'm using no parity, I only need to set bit 5 in this register, and all other bits can remain 0. For calculating the values which need to be written to the baud gen register and the baud rate divider register, we can take our desired baud rate and we can choose a value for the baud rate divider register. The baud rate divider register will have 1 added to it and has a minimum of 4 for division. I'm going to choose the value 6 would get 1 added to it to create 7. So we can multiply the transmit clock rate, which is our final baud rate, 115,200, by that. Multiply that by 7 gives us 806.4 kilohertz. Then to get the baud gen value, we just need to take 100 megahertz, the first clock, and divide that by the baud gen, or divide that by our RX clock rate to get the divider value necessary. So for the baud gen register, we need to write 124 to it, and for the baud rate divider register, we need to write 6 to it. Okay, let's look at writing an assembly program to configure and send a character over the UART. So I have a main program written which calls two subroutines. One is UART1 init, and the other one is UART1 setbaud. UART1 init initializes the UART module by writing to the control and mode registers, and UART1 setbaud takes two parameters. R0 is the value to be written to the baud generator register, and R1 is the value to be written to the baud rate divider register. The two values shown here are placeholders, and they'll be replaced with actual values. It's suggested not to use these. So let's have a look at the init function. So in my UART source file at the top, I have macros to the base addresses or the addresses of the registers in the UART module. These correspond to the ones found in the Zynq technical reference manual as well as on Real Digital's website. So I've declared both these functions I'm going to use as global, so I can call them in my main program. And in the UART init function, the first thing I do is call another subroutine which resets the module. So, as described earlier, the process to do that is to write 1, 1 to the first 2 bits in the control register, and then pull that until those clear. So that loop just loads the value in the control register and makes sure the bottom 2 bits are clear before proceeding. After that returns, the mode register is configured, and the only setting that wasn't at its default value was no parity, and that's accomplished by writing to bit 5. So 0, 1, 2, 3, 4. Bit 5 is set to 1. The control register is then used to enable the receiver and transmitter, so that's writing to bits 2 and 4. In the set baud function, the parameters are just written to the respective registers. So as we had gone over in our calculation earlier, the baud gen register needs to have 124 written to it, and the baud divider needs to have 6 written to it. It's potentially a good idea to set up constants so you can have multiple baud rates defined. So for our purposes, we're going to create 2 constants, one being baud gen 115200, set that to our value, and the other one being baud div 115200, and set to the other value. These can be put in place in the code. Okay, let's look at writing a function to transmit a character over the UART. Transmit a character over the UART, you need to write a character to the transmit FIFO. So the transmit FIFO is accessed at address offset 030 from the base of the module, and writing to that enqueues a character into the data FIFO, or into the transmit FIFO. Reading from it will take a character off of the receive FIFO, provided there's data. And similarly, if you write to the transmit FIFO, you need to ensure there's room on the FIFO first. To do this, you need to check the status of the FIFO through the status register. So the status register contains bits pertinent to the status of the UART module. In particular, the 2 bits we're interested in are transmit FIFO full status, which is bit 4 in the status register, and receiver FIFO empty status, which is bit 1. So transmit FIFO full status, if that bit is set to 1, the FIFO is full, and it will not accept any data from writing to it. So before you write a character to the transmit FIFO, you have to make sure that's 0. Similarly, the receiver FIFO empty status, you need to make sure that's 0, meaning there's a character in the FIFO before you can read from it. Okay, let's get started on writing our function. So we'll go into our UART source file, and we'll start writing a function UART1 put character. And at the end of it, we'll return, obviously. And to send a character, we need to pass data into it. So we'll have it have a parameter in R0, and we'll have it transmit character in R0 over UART. Right. So the 2 steps our function need are wait for room in the FIFO, transmit FIFO, and then write to transmit FIFO. Okay, so to wait for room in the FIFO, we need to pull it until that status flag is 0, the transmit full status flag. So we'll need a loop for that. We'll create a tx pull loop, and at the end of the loop, go back to that label. And instead of checking the status flag directly, I'm going to write a secondary function for readability. So UART1 tx ready, we'll call it. And that will return 1 in R0 if ready, and return 0 otherwise. So to do that, we need to read from the UART status register. So we'll load that address in. And we'll load from the current status from the register. So we just need to check if the transmit full flag is set. So we just need to put a bit mask to R0 and set the condition flag if bit 4 is set. And if bit 4 is set, the equal condition will be satisfied, or the not equal condition will be satisfied, meaning the transmit FIFO is full. So the not equal condition, place in R0 or return value 0. So if the equal condition is satisfied, the bit has been cleared. So we want to return a 1, meaning the transmit FIFO is ready to have a character enqueued into it. Okay, so now in our pull loop, we can call that subroutine. And compare the result, which will be placed in R0, to 1. And if the result is not, or if the result is 0, we can pull continuously. Or the result is not equal to 1, rather. Okay, so because we're using R0 in our new subroutine, we need to back up the old R0, which holds our transmit character, into another register. So we'll move that into R4, which is a saved register, but also means we need to back up R4. But we also need to back the link register because we're making a nested subroutine call. Okay. So now that'll pull until the flag is clear, until there's room in the FIFO, and then the program will proceed. So down here, we just need to write into the data FIFO, or the transmit FIFO. And just we need to store the value or character into that, which we've moved to R4. At the end of routine, we restore R4 and then we return. Okay, so let's declare that as a global function so we can access it in our main. And then we can call it from our main function. And we'll provide it with a parameter, a character to send, and we'll give it a character K. So let's have a look at the Vita serial terminal first. So in the debug view, typically the serial terminal will be found at the bottom in this tab here. If you can't find that, you can go to Window, Show View, type in Terminal, and it should show up there, Vita serial terminal, and we'll open that. So I'm going to move it up here so we can see it better. And here you can open a serial port, open a connection to a device. So we'll do that here. And on Linux, the Blackboard will show up as a TTY device for the UART USB bridge. On Windows, it'll show up as a COM port. So for me, it's TTY USB 1, and here you need to make sure the settings match what we programmed the board for earlier. So that's 115/200, 8 data bits, 1 stop bit, no parity. There, we're connected. So we're ready to run our program now. So we're going to hit debug. And we can step through. So we'll go through the init function, do the reset, set the baud rate. We'll load our character to be sent. Then we'll call the send character function. It'll check the status flags. And then it'll write to the data FIFO. And you can see in our terminal the character has been received by the PC.